Ready? Well, good morning. This is Construction 4060. We're going to do the next lecture, which is going to be on footers. I'll have a handout in your files section of Canvas. It should say Design a Foundation System, Wall Footers and Column Footers, Chapter 16. Okay, first of all, I want to make sure you understand what the footers are. And then today we're going to go ahead and design one with a wall footer. You guys are going to be doing 16.2b for homework, and I'm going to today do 16.2a to show you how to go about it. Okay, let's give you the concepts. The concept of footers are that the foundation has to have a foot, just like you have a foot that rests against the ground. So we are going to have three components to worry about. First of all, we've got to make sure that the dirt is fine. So this is foundations or footers. The dirt's okay, so we've got to stand on something that's solid. If you stand on concrete or asphalt versus quicksand, there's a big difference. So we've got to have a solid foundation or make the bearing area big enough so that it doesn't sink into the foundation. This foundation doesn't sink into the substrate that's holding it up. So we're going to have dirt, then of course the footer or the foundation is going to be made of concrete. And then when we deal with concrete, we also have the brother to it that goes along with it as rebar. Okay, so we're going to have three different types of materials: dirt, concrete, rebar. We have two different design philosophies. This one here, dirt, we're just going to use service loads. That's the allowable stress design. Service loads. No multipliers. No 1.6, no 1.2, just whatever the loads are. This, we're going to use a load and resistance factor model. So 1.6 live, 1.2 dead is going to go there. So service loads, no multipliers. No multipliers. Okay, so we got to worry about this thing breaking and sinking. So it could fail by breaking, or it could fail by physically not having enough area so that it sinks. So a wall footer, if you have a foundation, a basement, got a wall going all the way around, this is the footer. The footer is below the wall. It is the unit that sits directly against the dirt. So if I drew this in elevation, you would have something that looked like that. This line and this line are the wall. This line and this line are the footer. Okay, needless to say, the width of the footer is a direct related to the type of dirt we're sitting on. The better the dirt, the skinnier the footer. There is some minimum limits, but the heavier the loads and the worse the dirt, if the dirt is not quite as good, the width starts getting wider and wider. So we've got some things. If you read on the handout when you get it in your hand, the minimum width is typically 2 times the wall thickness. So a typical footer underneath the wall has this as a minimum dimension. The thickness of the footer is the same as the thickness of the wall, and the width of the footer is a minimum of twice that wall thickness. So if I have an 8-inch wall, my footer is typically 8 by 16. If I got a 1-foot wall, my footer is 12 inches by 24. So that's minimum. So it says right there. I need some edge distance. Okay? this distance has to have a minimum. And it says right here, it's 2 inches. If you look at it, 2 inches for masonry and 3 inches for a concrete wall. So we've got some code minimums. You just make sure you follow those. Another thing is we've got to make sure that what's underneath here is soil that hasn't been played with, tampered. That is a virgin soil. Means nobody's dug it up and threw it back in the hole. How do you look at it? Look for beer caps, cigarette butts, pop cans, anything that looks like it shouldn't be there and is means that someone put it there. It means it's been dug up and filled. It's not virgin soil. So make sure you're sitting on something that is solid and something that's not been tampered with. If it has been tampered with, we have to put it back in engineered layers. So it's called engineered fill. It takes quite a bit of time, quite a bit of energy, and it's costly. But it has to sit on something solid. If this structure is sitting on something weak, the foundation's bad, we end up with a structure that's totally worthless. So make sure you got that. We also have to have this guy a distance below grade. So if this is grade, ground level, regular normal dirt or asphalt or concrete, we've got to have a distance there that gets us below frost. So this has got to be a minimum for frost. So if the frost gets underneath the footer, when water freezes, it expands. When it expands, it pushes. We can move a foundation pretty easily with hydraulic force based on a frost situation. So we don't want that. Okay, they also have a minimum thickness for the footer. These are minimums, 8-inch and 10-inch. Without reinforcement and with reinforcement. Residentially, we don't use rebar a whole lot unless the site is relatively weak. We have spots that are really good and then other little spots that maybe the soil is moving, weak. We'll put rebar in it to bridge over those soft spots. So in our area, this frost is 3 feet, so depends on where you're at. Some areas, Florida, you're building in Florida and you talk about frost, they're going to look at you like you're a fool. They don't have to worry about that sort of thing. Okay, and then we've got rebar we're going to put in this little sucker. And the rebar has got to have cover. And that cover, we'll talk about it in our handout, but it's 2 inches if the material is formed. So if we form the sides and then pour it, this distance has got to be 2 inches. If we lay it against the dirt, we don't normally form the bottom of a footer. If it's laying against dirt, no form, so it can vary. This has to be a little bigger, and the cover there moves to 3 inches. So, form 2 inches, cast against earth 3 inches. And I think that pretty much takes care of that first sheet on that handout. What we're going to do now is I'm going to draw a cross section. We're going to tell you how we're going to do this, and then we'll do the problem. So the wall footer is one that fits underneath a wall. The next lecture is going to be a spread footer or a pedestal footer. That is a little different. Now this has several names, okay? I've used wall footer. So if you see any of these words, you're talking about the same thing. Wall footer, continuous footer, strip footer, they're all exactly the same thing. So don't get all bent out of shape that you've not heard that word. It's the same thing. Okay, the difference between this and a spread footer, if I have a basement, I have posts in the basement. I pour a slab. I set a post on top of it. And that is called a column footer, a spread footer. Those are the two most common things that I've heard. The cross section looks exactly like this. If I draw cross section, unfortunately they're different in length. A wall footer goes on forever. A spread footer has a finite width. And in our course, we make the width and depth of the footer. Width this way, depth that way, exactly the same. So we're going to be designing square footers, not rectangles. There are rectangles, there are trapezoidal ones. There's several types of spread, but we're just going to focus on a square. So, okay, we've got the three media. We've got the basic concepts associated with it. This is the wall thickness. This is the depth of the footer. This is the effective depth of the footer. This is H. D is the distance from the top to the middle of the rebar. We've got the width of the footer. We've got the width of the wall. And other than that, I think that's about all you need. So I'm going to draw the picture. I'm going to read the problem. We're going to populate whatever we have in the picture. And then we're going to calculate it. And I am going to use problem 16.2a. And when we read the statement, I'm going to tell you that you're not going to have to worry about some of this stuff because I'm going to give it to you in class. Okay, I'm going to draw it over here. There's my wall. There's my footer. And of course, the wall should set in the middle of the footer. Okay, if it doesn't, I've seen them where they're not. Foundations or footers aren't meant to be eccentrically loaded. The load's supposed to go right down through the center. So I'm going to put some letters here. This is W. This is WT. This is H. And the rebar is going to go through here. And that is D. Okay? So I've got formulas, a lot of formulas in here. Unfortunately, some of you need formulas to make it through life. I'd rather have you use your head and think, okay, rather than just randomly put numbers in a formula. So I'm going to explain it logically, and hopefully you can follow me related to the table. So I've got 16 point. A wall footer, 16.2a. Okay, let me read the problem. We're going to put everything we've got up here, and hopefully when we get done, we've got enough to solve for what they asked for. Using the concrete strength of 2,000 psi, FC prime. It's got 40 grade steel. Fy is 40 ksi. Wall footing, wall thickness, 10 inches. Dead load, 5,000 pounds per foot. Dead load, 5,000 pounds per foot. Live load, 7,000 pounds per foot. And the soil bearing capacity maximum 2,000 pounds per square foot. So that is the value you would get in your life from a soils report. A geotechnical company would go out, They would grab a sample out of the site, they would take it back to the lab, they would analyze it, and when they got done, they would generate a report, and sigma max is how we. So that soil can handle 2,000 pounds per square foot. That's pretty weak, okay? A 2,000 pounds per square foot soil is what we use as our benchmark for residential. It's a pretty weak soil. As opposed to something like bedrock, 20,000 pounds a square foot. Good clay, 3,000, 4,000 pounds a square foot. So you've got various types of soils. So let's grab your handout. You should be on number 1, design procedure for a wall footer. It says letter A, determine the thickness of the footer. There's a table. You can put Joe will do this. I'm not going to have you look at a table and try to figure out the thickness. I'm going to give that to you. And for my problem, I'm going to use H equals 18 inches. So this will be a Joe right here. You won't have to worry about using that table. And I'm going to give you the height for the problem you have to do, which is 16.2b at the end of the lecture. Okay, so there. I will also give you the bar size. Okay, so the main bar size I'm going to give you as being a number 5 for this particular problem. Okay, so that's number 1. Second one, we want to know how much that footer is going to weigh. Why are we doing this? I'm in dirt now. So I'm going to do dirt. I want to figure out how much load is on the dirt. That's comprised of 2 things. The first thing it's comprised of is the weight of the footer. The second is the load we're putting on it. So letter B is to determine the weight of the footer. So H equals 18 inches given. Weight of footer. Unit weight of concrete is 150 pounds a cubic foot. The height divided by 12 changes the 18 to feet. Feet times feet, pounds per cubic foot, is going to be pounds per square foot. So weight of footer. 150 pounds a cubic foot. 18 inches divided by 12 inches per foot. So the footer weighs 225 pounds a square foot. Let's subtract this weight from the soil bearing capacity to get sigma net. So C, sigma net is equal to sigma max minus footer.